So I try to finish it today itself, but we'll see what happens. Or if needed, maybe tomorrow I'll finish it. So in the last class, I was discussing about MM1 queuing model, no? MM1 model. So that means basically interval time has a Poisson distribution with parameter lambda. Service time is again exponential distribution with parameter say mu. And then you have only one service counter. Okay, so number of service channel is 1, an infinite queue. Sorry, and the capacity of the system is infinite, and it is FIFO, first in, first out. That is the queue. Okay, so there what we have seen that that if row I am defining, which is my lambda by mu, which is less than 1, then we have seen that the stationary distribution would exist for lambda, the row less than 1. That means lambda by mu is less than 1. And not only that, we also consider some important measurements, in particular, what is the average time in the queue, and also what is the average number in the system denoted by LS, and then the average number in the queue denoted by LQ, and then using the little formula we have considered basically LS and TS, what is the average number of means time spent in the system TS and also in the queue TQ. Okay, so basically LS, which is a lambda effective of T of S. So what is your lambda effective? That is the long-term average arrival rate. Okay, so now you will see that in this case lambda effective is equal to lambda because of the infinite queue and so on. But whenever if you have some system capacity, so there actually you'll see that there is a concept of blockage that customer cannot enter. Okay, suppose I have a system which capacity is say capital N. Okay, and then so if it is full, that means we are not allowing the customers to arrive. So that means it is a blockage. Okay, and so this is happening in pi of n if the stationary distribution exists for that, and then this effective arrival then is lambda times 1 minus pi of n. Okay, that we'll see it, because an arrival customer gets entry if the system is not full, then actually it can entry, no? So that means the arrival rate, which is lambda into 1 minus pi of n, because this state probability, which is the pi of n, this is the blocking probability, because if the customers are blocked when the system is in state n, means whenever system is completely full, and then actually you are not allowing the customers to arrive. That means the blocking probability. Okay, so not only that, we have discussed about the random time t, which is the total time spent by a customer, and what is the probability distributions of that, and also the spend time or the waiting time of the customer in a MM1Q model. Okay, so today we'll talk about many different model. One of them is, in particular, this is MM1N queuing model. What it is? So again, this is a queuing system always. That means it is a queuing system. So M denotes, that means basically the both inter-arrival and the service time which follows the exponential distributed distributions with parameters say lambda and mu respectively. And this one, it denotes basically we have only one service channel. Okay, and this n, what it says that only n customers are allowed in the system. Okay, so the infinite queue with at most n customers are allowed in the system. So if I denote my xt, where xt denotes the number of, say, customer in a system at time t, then this MM1N king model I can think of, it is a birth and death process with birth rate lambda n, which is lambda for n should be 0, 1, 2 up to n minus 1. And what is your death rate mu n? That should be mu for n is equal to 1, 2 up to capital N. Okay, so if I try to look at the state transition graph for MM1 model, how it looks like. So this is your say 1, 2, 3, and so suppose this is n minus 1, n minus 2, and so on. So what it says that 1 goes to 2 with lambda because birth is happening, the birth is happening, and so on. So now this is lambda, this is lambda. Okay, so that means death is happening, so on, death is happening, and then death is happening. Is it not? So this is the state transition graph of my MM1N model. So basically what it says that this is a queuing model with inter-level distribution is exponential with parameter lambda. Service distribution is again exponential distribution with parameter sum mu. We have one service channel and the capacity is basically capital N. Okay, so that means what it says that when there are n customers in the system, that means the one customer is under service and the remaining n minus 1 customers are waiting in the queue, then new arriving customers are blocked. Is it not? That's I'm saying that because if it is full, then we are not allowing the customers to arrive. That means it is blocked. Okay. So now it is a finite state space. No, I can think of 0, 1, 2 up to capital N, finite state space. And then already we have seen that for a finite state space, the stationary distribution exists for birth and death process. So if I denote pi, which is my pi 0, pi 1 up to pi of capital N, this is the stationary distribution. This exists now because of our previous theory. So then what I know, what will be my pi of 0? Pi of 0, this is equal to 1 plus that summation over n is equal to 1 to capital N. Now we have product of I is equal to 0 to n minus 1, then lambda I by product of I is equal to 1 to capital M small n of mu I. Is it not? That inverse. So now these things actually I can write down. So now this is, you have your lambda and then this is mu, and we have defined already rho, which is lambda by mu. Then this is nothing but 1 plus summation over n is equal to 1 to capital N rho to the power n, and then inverse. Is it not? So now it's depending on the rho, I can have this sum. So this is 1 by 1 plus capital N if my rho is equal to 1, because if rho is equal to 1, you have n number of things. So this is basically 1 plus 2 plus, no, if rho is equal to 1, then what means basically 1, 1, 1, 1 n times. So you have n, and then I have 1, so this is 1 by n plus 1. Now, if my rho is not equal to 1, so now you see that this is a, the geometric series but with finite term. So then what I know from there, this should be actually 1 minus rho to the power n plus 1, that sum, no? Summation over n equal to 0 to capital N, rho to the power n. What I know? Summation over n is equal to 0 to capital N, rho to the power n. This is, we know that 1 minus rho to the power capital N plus 1 by 1 minus rho, no? This part we have for rho not equal to 1. So now this is exactly same as my this part. And then inverse, so this is 1 minus rho by 1 minus rho to the power n plus 1 for rho not equal to 1. Is it not? This part actually we know. And so I have my this part. And so in that case, what will be your the state probability pi of n, again in a stationary case, that means in a long run. Is it no? Stationary case means in a long run. So what is your pi of n? Then we know that pi of n is equal to exactly that inside things. Is it not? Inside things. This is my pi of n. So what you have, this should be 1 by n this should be 1 by 1 plus n if rho is equal to 1, and then this is 1 minus rho times rho to the power n, okay, into pi 0, no, into pi 0. Pi of n is equal to this part into pi 0, this part into pi 0. So then I have rho minus rho to the power 1 minus rho to the power capital N plus 1. So this is for rho not equal to 1, and this holds for all n is equal to 0, 1, 2 up to capital N. Isn't it? This is my state probabilities. So now, as I said that this probability is a pi of n, state probability pi, and this is called the blocking probability. So pi of n, this is called blocking probability. Why this is so? Because the customers are blocked when the system is in state n. Is it not? So that is why it is called the blocking probability. So that's I'm saying that means the arrival customers get entry if the system is not full. Is it not? So the customers are arriving, they can get into the system only if the system is not full. So then what is the effective arrival rate in that case? So not full, that means this is my blocking probability. So 1 by pi of n, and then the effective is now then the lambda times, because the customers are arriving in a lambda with rate lambda. So what will be the your lambda effective in this case? This is lambda times 1 minus pi of n. Is it not? When the system is empty, it's not empty. So 1 minus of pi of n, and then lambda times that part. Okay, so this is the long run average effective arrival rate. So as I said that if you have a say infinite, so in this case you have n capacity. That is why that lambda effective is different from your arrival rate. Because in your previous case, since the capacity of the system is infinite, so it does not matter. So effective rate is basically same, is it not? But in this case, the effective arrival rate is depending on my blocking probability, which is lambda times 1 minus pi of n. Okay, so like in previous case also, here also we try to know what will be the average number in the system. So L of S, is it not? So what is L of S? L of S we define that average number in the systems. So that should be summation over n is equal to 0 to n. This should be capital N, no? N times pi of n. Now if you calculate these things, what it will be? this is, so summation over n is equal to 0 to capital n times, so now pi of n, I have two things, no, this is rho to the power n of 1 minus rho by 1 minus rho to the power capital N plus 1 for rho not equal to 1, and this should be summation over n is equal to 0 to capital n times, in this case, pi of n, which is n 1 by n plus 1 for rho is equal to 1. Is it not? So now if you do this calculation, then what I have, so from here what I can write down, that I can take common rho into, so this is rho into 1 minus rho summation over, so I can put up n is equal to 1 to capital N. Now n times rho to the power n minus 1, okay, and then I can take also 1 minus rho to the power capital N plus 1 for rho is not equal to 1, and in this case, so now I have, this is n is equal to 0, 1, 2 and so on. So this is what I call, so this is the sum of no s n is equal to 1 plus 2 up to small n, that we know that this is n into n plus 1 by 2. So from there what you have, this is capital N by 2. Is it not? So now if you just simplify this one, previous one, so already we have seen that what I have seen, that 1 minus rho to the power n plus 1 by 1 minus rho, which is summation over n is equal to 0 to capital N rho to the power n for rho not equal to 1. So now the term by term differentiations is allowed here. Now if you do it, so then this should be, if you differentiate it, so do rho of 1 minus rho to the power n plus 1 by 1 minus rho, this is nothing but summation over n is equal to 1 to capital n times rho to the power n minus 1. Like in previously, we have done the similar kind of idea there. So now if you do these calculations and then if you simplify it, so what you end up with, this should be rho by 1 minus rho minus n plus 1 times rho to the power n plus 1 by 1 minus rho to the power n plus 1 when rho is not equal to 1, and then this is n by 2 if rho is equal to 1. Okay. So what it says, that the LS, which is the average number of customer in the system, is given by these things. So then what will be the average number in LQ? So you can do again using this formulation. Okay, because since you have only one channel, then n minus 1 is there. Or on the other hand, you can check of LQ, this should be LS minus lambda effective by mu. Okay, it should be lambda effective by mu. So you can calculate that part, or otherwise you know the definitions for L of Q. Is it not? That should be basically from n is equal to 1 and then to n minus 1 I have. Like in my previous case, no, because at the system at most you can have, you may the total number should be n, and hence in the Q it should be capital N minus 1, and then the row n you have a pi of n. So from there also we get it, that rho Q is equal to LS minus lambda effective by mu. Okay, check yourself this part, this calculations from there, and then again using the that little principle, what I have, or the little formula, what I have, that L of S. So from there I have LS already I have find out. L of S is equal to lambda effective of T of S. No, the time spent of a customer, and the average time spent of a customer in a system, and then what I know, that L of Q, that should be the lambda effective of T of Q. So I know LQ, I know LS, and hence I can find out my TS and PQ from this system. Okay, so basically what is important here to understand your the state probabilities, in particular the stationary probabilities, okay, stationary distributions, when it exists and how the state probabilities pi n looks like. Because as long as you know that part, all these things can be deduced from there using our formulations, is it not? And also the Little's formula, you can find out the average time spent in a queue, average time spent of a customer in a system by using the lambda effective. So in this case, lambda effective is nothing but lambda times 1 minus pi of n, because pi of n is the blocking probability, because if the system is full, that means n minus 1 customers are waiting in the queue, then the customers are blocked. No, the arriving customers are blocked, and hence the effective rate of arriving customer is basically lambda effective, which is lambda times 1 minus pi n. Okay, let us consider one simple example, and then so what it says there, suppose that we have a motor car repairing center, and then the customers are arriving to that repairing center. And so now suppose the time spent on a repairing of a motor, it follows the exponential distribution with mean 40 minutes. Okay. And suppose in that shop or in the garage you can think of, so they are maximum say 9 motor cars, including the one under repair. So that means my capital N in this case is 9. Okay. So now cars are repaired in order in which they arrive, and the arrives can be approximated by a person process with an average rate say 15 per 10 hours. So what it says that, so you have a garage, and then the customers are coming to repair your motor or the cars. Okay, so now the spend time or the repairing time, what it says that repairing time follows an exponential distributions with mean 40s. That means my mu, which is equal to 1 by 40 in this case. And then the arriving rate, what it says that the arriving rate at approximately person process with an average rate of 15 per 10 hours, 10-hour day. So that means that lambda in this case, what it says that, so in 10 hours you have your 15. So now I need to put it in a minute. That means in 60 minutes you have 15 car, or the 15 in average. So that the lambda should be 15 by 600. So this is actually 1 by 40. So lambda is also in this case 40. Okay, so I can then modify the things that, okay, so the service time follows exponential distribution with rate mu, which is 1 by 40, and then the interval customers or the interval distributions is again exponential distributed with parameter lambda, which is 1 by 40. Okay, and again these things actually we can model it by MM1N Q model. Here n is equal to 9, because as I said that at most n cars can be accommodated in that garage. Okay, so now what is the question? So what is the probability that the repair person being idle in the long run? Okay, so that means basically idle means lazy, or in the sense that means if you are waiting, then you are not lazy, no? You are working in that case. So that means I need to find out. Okay, so maybe write down the question. Then what is the probability of the repair person being idle in the long run. Okay, so that means what actually I need to find out that in a long run probability of repair person being idle, that's nothing means the pi 0. Is it not? That is means the pi 0. So then this is nothing but I need to find out the pi 0. So what is pi 0 in this case? Pi 0 is equal to 1 by 1 plus n if my rho is equal to 1. So in this case, you see that rho is equal to 1 because rho is equal to lambda by mu, which is 1. So the probability that the repair person being idle in the long run is nothing but my pi 0, which is in this case 1 by 10, which is 0.1. Okay. So now my second question is to find the portion of time that the shop is not full in a long run. To find the portion of time the shop is not full in the long run. Means what it says that basically not full means basically the suppose the customers are arriving to repair their car, so that whenever it is completely blocked, then actually he can go back. But if it is not blocked, he can go there. So that this is the what portion of the time means what are the percentage in a long run that customers can enter to the system. Is it no? That my shop is not full. That means he can enter to the system. So that means what? The system which is not full, as I discussed, that it should be nothing but in the long run, it is 1 minus pi of n. So in this case, this is 9. Is it not? So the probability that the system is not full. So now rho is equal to 1, I have. So if rho is equal to 1, here if you see it, yeah. If rho is equal to 1, then pi of n is equal to 1 by n plus 1, which is actually same for all. No. So for rho is equal to n, pi of n is equal to my pi of 0 for all n is equal to 0, 1, 2 up to capital N. So hence 1 minus pi of n, this is nothing but 1 minus pi of 0, and pi of 0 already we have, so this is 1 minus what I have, that 0.1, no? So this is 0.9 then. So that means basically the probability that the system is means the system is not full, the possibility is 0.9. That means 90% time, is it not? So if I say that what portion of the time means automatically they are asking that what is the percentage, is it not? I can think of. So that means 90% of the time the shop is not full in a long run. It is not that just you are looking for say first 2 hours and then you are discussing. No, because all these pi n, which is basically the stationary distribution, that means in a long run, okay, we can say that the shop is not full 90% time. Okay. Okay. So next we will discuss about, so all this, the model whatever we are discussing here is just first we need to know whether the system has a stationary distributions or not, or under what conditions we have stationary distribution. Because if we have a stationary distributions and all these things, then actually we can talk about these measurements, no? What are the average number in a queue, and what is the average number in a systems and so on. So I need to understand whether or under what condition system has a stationary distribution. Okay. So next I will talk about, this is called MMCQ. So first I talk about C is equal to 1, only one channel. Okay, number of service channel is 1, but here what I'm saying, that I have C channels. Again, the interval distributions is exponential distributed with parameter lambda. Service time distributions is exponential distributed with parameter mu. We have C number of channel, but the infinite capacity. So that's why I not put as infinite. So infinite capacity is there. Okay. So it's a queuing system with arrival according to Poisson process with rate lambda, and service times follows a exponential distribution with parameter mu. See the service with infinite system capacity. So now what I know, that in this system, whenever customers are arriving, suppose it is n customers are in the systems, and then if n less than c, because I have c channels, c service channels, so if n less than c, it is automatically routed to any idle server, means who is not busy, is it not? But if in the system, if it is more than c, then you have to wait. That means you are standing in the queue. Okay, you join in the waiting queue. Is it not? Because you have C channel. So customers are arriving. So as long as in the system, suppose it is n. So if n less than c, suppose this is working, this is working, this is working, that time. So you immediately send to the headless server, means who is not working. So you just immediately there. So now if in a system, suppose I have n number of people or n number of customers at time t, and then which is greater than c, that means n and c number of customers are serving at that time, and then you have to join in the queue. Is it not? So in that case, if my xt, if I denote again the number of customers in the system at time t, then this MMC queuing model is a birth and a death process with birth rate lambda n, which is lambda for n is equal to 0, 1, 2, 3, and so on. But then what is the death rate? This is n times mu. Okay, for 1 less equal to n less than equal to c, and then as long as you have c server, so this is c of mu for all n greater equal to c. Okay. Okay, because at the same time you are going to at c, more than that you cannot do this. So that means if I look at my, yes, if you just look at my state transition diagram for this MMC queuing model, so now here the state space S is infinite, is it not? The system capacity is infinite. So suppose this is 0, 1, 2, 3, so on. Say suppose I put as a, this is C channel, C plus 1, C plus 2, and so on. Okay, so 0 goes to 1, you have lambda, you have lambda, you have lambda. So now whenever you are having here, then what I have basically, this I have 3, that if I have a 3, this is I have 2 mu. Okay, 3 goes to 2, I should be 3 mu, this should be 2 mu, this goes to mu. That is why I have that mu lambda, and so on. So now here I have C. So C plus 1 to C, this is basically same C mu. Okay. And then if I have here, this is also same. I have C mu, but from here to here I have C minus 1 mu and so on. And then here I have C mu. But in this case, this is also lambda, this is also lambda, this is also lambda, and so on. Okay, so this is the state transition diagram for MNC queuing model. Okay. Okay, so what it says that this MMC queuing model is a birth and death process with birth rate lambda n is equal to lambda for n equal to 0, 1, 2, and so on. And mu of n, which is equal to n of mu for 1 less equal to n less equal to c, because I have c number of channels, c number of service channels, and this is c of mu. After that, it is constant, that is n greater equal to c. Okay, so in this model, whether the stationary distribution exists or not, so stationary distribution, this exists.
Excuse me, sir.
Yes.
So can you please explain mu n?
Second?
Mu n.
Yeah, mu n. Mu of n is equal to n times mu. Okay. For 1 less equal to n less equal to c. And then after c, because you have n c number of channels, no?
Yes, sir.
You have a c number of channels. So if n is greater than c, then actually the rate is basically fixed, the death rate, which is c times mu. Is it not? Because you have a c number of channels. Because if n is less than c, you can immediately go to for your service.
Right, sir.
N means basically I'm saying that if at time t, the number of customers in the system is n. Is it not?
Right, sir.
So that you can go there, no? So that is why that n mu times is there. But after, if it is bigger, you have to weight it. So that's mean the death rate should be the, according to that, no? C times mu.
Okay, sir.
You have to weight it. Okay. So this is the stationary distributions for pi. It exists. You check that if the rho, which is by lambda by mu, okay, if this is less than my small c. So the condition is that the stationary distribution pi is equal to pi I. So I belongs to my state spaces. In this case, it is 0, 1, 2, and so on. This is the set of natural number, including 0. Then if rho is less than c, then the stationary distribution exists. Okay, so again we have already write down, no, stationary distribution when it is exists, that pi 0, that infinite sum, whether it is convergent or is it not? So it said from there that if rho is less than c, that means my lambda by mu is less than c, then always stationary distribution exists. Okay, so in that case, that means suppose my rho is less than c, then how my state distribution, that means pi n is given by, so pi of n, that should be your rho to the power n by n factorial of pi 0 when n less than c, and rho to the power c by c factorial, then rho by c to the power n minus c of pi 0 for n is greater equal to c. Is it not? Because what is your pi of n? By definitions, pi of n, this is product of I is equal to 0 to n minus 1 lambda I by product of I is equal to 1 to n mu I times pi of 0. Is it not? This is the general case. So from there actually I just put it for n is less than c, then I know that lambda and mu, so you see exactly this kind of things is happening. Okay. and that n factorial is coming because of your these conditions n mu for 1 less than n less equal to c, and then I have that c factorial is there, so it is coming like this. Okay. Okay, so this is my pi of n, but I need to find out my pi of 0. So again, what we know? We know that summation over I is equal to 0 to infinity. Pi of I gives you 1. So from there, you just try to calculate what will be my pi of 0. This should be summation over I is equal to 0 to c minus 1 rho I by I factorial plus rho c by c factorial c by c minus rho. Okay, the inverse. Okay, these are the things pi 0 one is to calculate it using your c and then and all these things for particular c. This is my pi 0 and then pi of n these things. Okay, so here one thing is that, so what is the probability that the arriving customer has to wait on arrival? That means it is nothing but actually summation over n is equal to c to infinity pi of n, no? Because you have c channels, so pi 0, pi 1, pi 2 up to pi c, so he has to wait, that means sum over that part. So the probability that an arriving customer has to wait on arrival, this is summation over n is equal to c to infinity of pi c, sorry, pi of n. Is it not? He has to wait it, means he has to join in the queue. We have only c number of channels, so this is the things. And now if you calculate it, this should be summation rho to the power c by c factorial pi 0 and c by c minus rho. So this is actually is my pi c. So if you see from here that pi of c is nothing but rho to the power c by c factorial times pi of 0. Okay, so rho to the power c by c factorial pi of 0, this is pi of c by c minus rho. Okay, so the probability that the arriving customer has to wait on arrival, this is given by pi c times c by c minus rho. Okay, this is sometimes called the Erlang-C formula. Okay, so this is the probability that customer has to wait. Okay, so as long as we have the stationary distributions and so on, we can talk about again what will be the LQ, LS, TQ, and T of S and all these things. Is it not? So now you see that here that lambda effective is equal to lambda, is it not? Because you have infinite q and so on. So in a long run, lambda effective is same as your lambda. So what is your L of q, which is the average number of customer in a queue? That should be what? Basically, it should start from n minus c, no? Means c plus, if less than n, then there is no problem. N is less than c, then there is no problem. That means it should be summation for n is equal to c plus 1 to n, and then the remaining customer, which is basically n minus c. Is it not? Because c is served immediately, and so the remaining is n minus c and times of pi of n. Okay, in the same logic. So now if you do these calculations using your pi of n and all these things, then it will end up with pi c times rho c by c minus rho square. Okay, do the calculations using this you look at my pi of n, okay, and then do the calculation. So then actually it will be in this form, pi c times rho c by c minus rho square. Okay, as long as I have L of q, then what is my L of s? Ls should be nothing but Lq plus lambda effective by mu, which is, that means my lambda by mu. Okay, now if you calculate, this is pi c rho c by c minus rho square plus lambda by mu is nothing but my rho. Is it not? So I have Ls, and then you do the simplifications and so on. Okay, so now I can find out my TQ, the time spent, average time spent of a customer in a queue, TQ, which actually I can use again the Little's formula, which is lambda effective, means okay, LQ is equal to lambda effective times T of Q. So that means this is L of Q by lambda, which is L of Q. What I have, this is pi C, C by mu 1 by 1 minus rho square. Basically, I can put C here, and then do these things by lambda I have. Okay. C by mu 1 minus 1 by rho square. Okay. Now, what is the average time spent of a customer in the system? This is same as my L of S by lambda effective. Okay. So L of S already we have this part, that pi c rho c by c minus rho square by lambda, and then plus rho by lambda. So this is nothing but 1 by mu, no? This part, because lambda is equal to lambda by mu. So this is 1 by mu, exactly equal to. And this one is actually is equal to pi c by mu into 1 by c minus rho square plus 1 by mu. Okay, so which is exactly, now I have in this case TQ plus 1 by mu. No, in this case I have TQ, TQ is the same as this part, pi c by mu 1 minus c minus rho square. So I have this part. Okay, just use the Little's formula. From Little's formula we have this argumentation. Okay, so let us consider one example. And so basically in this case one is to do the calculations, because I have this sometimes infinite sum, sometimes finite sum. Whenever it is a finite sum, maybe one can directly use this formula and so on. Even for the infinite sum also one can use the formulations, but you need sometimes the calculator to do these things, is it not? But I think you don't need the scientific calculator. The normal calculator will help these things. Okay, so let us consider the example. First, I write down the example and then I'll discuss. Yes. सर वो एसी की सर्विस के लिए आए थे, वो बाद में क्लास चल रहा है. So consider a supermarket with 4 centers. Okay, so we have supermarket with 4 counters. Okay, so now I can think of what that in a, okay, so practically I cannot say that in a supermarket you can accommodate the infinite number of the customers. That is not possible, but you can, it is a big supermarket, so you can accommodate many people. So in that sense, actually I can think of this is MM4 queuing system. Okay, so in that sense, so now the customers, they are arriving on an average, say 10 customers every 6 minutes. Okay, So 10 customers arrive on an average of every 6 minutes. Okay. While in the counter, whenever people are serving at that counter, so the service time in counter takes an average 4 customers in 6 minutes. Okay. So cashier in the counter can serve on an average say 4 customers in 6 minutes. Okay. So again, we can assume that the arriving of the customers are following a Poisson distribution, exponential Poisson distribution. So with these things, and the service times is again follows the exponential distribution. So then, what is the question? Question is, what is the average number of customers in the queue and in the systems? So find LS and LQ. Okay, average number of the system and in the customer. And secondly, so what is the average time a customer spends in the system? So that means my T of S I am looking for. And third thing, it is little bit tricky, but you need some kind of numerical things that I'll tell you how to do this. So I need to find out what will be the optimal number of customers. Sorry, what will be the optimal number of cash counters on that shopping or the supermarket, so that the portion of time a customer has to wait is at most 50 seconds. Okay, so that means basically customer they should not wait more than 50 seconds. So what will be the optimal number of counters? See, if you suppose I need say capital A number of counters so that it is happening. You can have A plus 1, A plus 2 and so on, but I need optimal. In that sense, what will be the minimum number of counters, so that optimal in that sense, so that the customers in a cash counter they should not wait more than 50 seconds. Okay, so this is the question is kind of easy, but one needs to do some numerical simulations to compute that part. So I'll tell you how to do these things. Okay, so let us first try to find out these two things, first one and second one. So as I said that this system, I can think of that this is MM4 queuing model with interval rate lambda, which is my 10 by 6, and mu, which is 4 by 6. Is it not? Because 10 customers are coming in a 6 minutes, every 6 minutes. So 10 customers arrive in this thing. So lambda is equal to 10 by 6 and mu is equal to 4 by 6. So what is your rho? Rho is equal to my lambda by mu. This is 10 by 4. So this is strictly less than 4 because 4 is equal to now my C, in my case. So what I have, rho is less than C. That means rho is less than C means basically, just a minute. Since rho is less than C, the existence of stationary distribution hold. Okay, so we have stationary distributions pi, which is equal to my pi I. This exists in this case. Okay, that is important. So then what will be my pi of n? This should be, if you checked it, what I wrote down here, pi of n, yeah, this one, rho to the power n. So what is your rho? Rho is equal to 10 by 4. Okay, so 10 to the power n by n factorial times pi 0. Is it not? For n is less than c. So now c is your 4. So from there actually you can calculate n is less than 4. And then I have, so this is nothing but my 5 by 2, no? So I can have, this is 5 to the power n by 2 to the power n times n factorial, and pi 0, n is less than 4, and 5 to the power 4 by 230 to these things, 5 by 8 to the power n minus 4 of pi 0 for n greater equal to 4. And then what is my pi 0? So in this case, pi 0, you'll see what I have wrote down. Pi 0 is equal to this thing. So now c is equal to your 4. So now you can calculate this one. Okay, so it is approximately 0.074 approximately. Okay, so now with this pi 0, I can find out my pi of n in this case. So what is my average number of customer in the queue? LQ. This is by definitions n is equal to my c plus 1 to infinity n minus 4 times pi of n, no? N minus c times pi of n. And so these things I have already, I wrote down here. LQ, this is pi c, means pi of 4 times something. Okay, so these things actually you can write down pi 4 times 10 by 2 into 25. Simple calculations. So now again, if you look at your pi 4, this should be 0.120. You calculate it times 10 by 2.25. So this is approximately 0.053. Okay. So the average number of customer in the queue equals to this part. And the average number of customers in the system, which is ls, this should be nothing but I had lambda by mu, which is rho, plus, is it not? This is my rho plus LQ. This is now rho is 10 by 4, which is 2.5, no? And then plus I have 0.053, so I can have 2.553, something like that. So now I have ls. So using this ls, what I can find out, what will be my the average time spent of a customer in the system ts, that should be nothing but by ls by lambda. So ls already I know that this is 2.553 divided by lambda. Lambda is what? This is basically 10 by 6. This is 10 into 6. So you see that this should be approximately 0.531. Okay, you just calculate it. I have calculated, but I may made mistake, but it is something like that. Okay, so basically if you see that all these things, okay, so the last one is important. This is I want to say how it is looking on. So what I want to know, that what will be the optimal number of cash counters, so that the customers the portion of time a customer has to wait at most 50 seconds. Okay, so suppose I have a C counters. So whenever you have a counters number is C, then one condition you need row is less than C. Is it not? That is actually first you need. Okay, so one is to choose C greater or equal to 3. So from here, because row which is equal to 2.5, so that means my C should be greater or equal to 3. This is the first conditions actually I have. So now what I have to have, that the portion of time a customer has to wait at most 50 seconds. So that means my T of Q, which is average, the time spent, average time spent of a customer in a queue, that should be less than 10 seconds. Is it not? So time spent, it should be less than 10 seconds. So then this is kind of 0.1672 minute. Okay. So now I try to find out the trial and error method. So first you consider C is equal to 3. Then try to find out your TQ. Okay. So find C is equal to, consider C is equal to 4 and so on, and then find your TQ. C is equal to 5, so on, and then find your TQ. So at some point, if you consider that T of Q is less than say 10 second or 0.167 minute, so you do it in a same the unit. So since I put it as a minute, so you need to put it. As long as your TQ is less than 0.167 minutes, okay. So and here actually, so I have my C is equal to C1 and then C2 and so on. So suppose this is my C star in some way, so I put it C star so that this is less than 10 and then maybe I have greater than something else in this case. So now use the trial and error method in a computer so that you find your C star. Okay. So the optimal number of cash counter in your shopkeeper should be this C star. Okay, because the first conditions I am having that C is greater equal to 3, that is from your the condition that I should have existence of stationary distribution. So from there I am having this part, and from this one, because I want that the portion of time okay, the customer has to wait at most 50 seconds. So I need, that means my TQ should be less than 10 seconds. And so now for C you find out TQ, C is equal to 3. For C is equal to 4, find TQ and so on. Then if you see that, okay, my in this for C is equal to 4, TQ is less than 10, then you stopped it and then you say that, okay, I need at least 4C. So in that case, you just check it whether this is less than 10 point something or not, means whatever it is required. You just look at, okay, then you will find out this thing. So it's kind of the trial and error method in the computer. That means you just put a algorithm. Okay, so you choose that C whenever my T of Q is less than this part. Okay, so you will automatically do these things. Otherwise, you go C to C plus 1. Is it not? So it's like do and while method in a MATLAB. Mostly this has to do it in a MATLAB. So you write down the code for there, because you know the formula for that. You just write down these things and then you are asked that it is kind of, no, whenever the threshold is having, you try to stop it. So otherwise you go from C to C plus 1. Is it not? So while TQ less than 10, maybe TQ less than 10, you stop it. Otherwise go to C plus 1. Okay, so in that way, actually, you can find out your optimal number of cash counter in a supermarket, so that the portion of time a customer has to wait at most 50 seconds. Okay, so now I'll talk about one more and then I will stop it. Okay, there are many things, but as I say that we'll look at the Markovian model, simple Markovian model, all these things. So next I will consider that is called MMCK model. So particular C is less than K. Okay, so there is a one possibility that C should be less than equal to K. So in that case, actually, you just think of yourself what will be the case. Okay, but here I am saying that I have C channels. Service channels is number of service channels is C, but the system capacity is capital K, where C is less than K. Okay, so we consider MM1 N, no, 1N model. So now this is MMCK model. So in this case, again, it's a queuing system with arable, say according to Poisson process with parameter lambda, and say service time follows the exponential distribution with parameter mu. Okay, C serves with finite, capacity K or C less than K. So now again, if in this system the customers find n customers in a system, so then if n is less than C, then it is forced to not routed to an idle server, else it joins the waiting queue. Again in a same way. So now, and since the system capacity is K, so then the customers are forced to leave the system if there are K customers present in the system. Is it not? So in this case, you can think of again the blocking, the blocking probability, and here also one can think of what will be the effective rate of arrival. So the interarrival distribution follows a Poisson distribution response lambda, service time distribution, exponential with parameter mu, and then I have C number of service channel, and K is the system capacity. Okay, so you see that if n is less than C, then you don't need to wait. Okay, that means you don't need to join in the queue. But if n is greater than C, need to join in the queue. But since I have total system capacity is K, that means the customer should forced to leave the system if there are K customers present in the system. Okay. So the effective rate in this case, it should be again lambda terms 1 minus pi over K. Okay, like in your previous case, 1 minus lambda of K. Okay, so let us look at what will be your state distribution. Exactly same, the state transition diagram for this MMCQ queuing model, exactly same there. But here now, my state space S is finite. This is 0, 1, 2 up to capital K. So you have 0, 1, okay, and so on. Then maybe you have say this is my C, okay, this is C minus 1, this is C plus 1, and then I have K minus 1 and then K, suppose. So then I have, this is lambda, 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 so here I have lambda, I have lambda, and so on. But now if I in a system C, okay, then here I have C times mu. Here I have C times mu. Here I have C times mu. Because the death rate here C mu, okay, because you have C number of channels and total K capacity is there. And before that, what I have from here, this is mu. So from here, it should be your 2 mu. From here to here, it should be a 3 mu, and so on. So it's again a birth and death process with lambda n is equal to lambda for n is equal to 0, 1, 2 up to n. This is k minus 1, capital K minus 1. And then what is your mu of n? This is again exactly same thing else, n mu for 1 less equal to n less equal to small c, and then C mu for C less equal to n less equal to capital Q. So there we have put C less equal to n, but this is, since I have K capacity, so this is less than equal to K. And so in this case, always stationary distribution exists, no, because it is a finite state space. And so stationary distribution exists. So pi is equal to pi 0. So I belongs to S, which is 0, 1, 2 up to capital K. Okay. And what is your pi of n in this case? You can see that this is exactly same. No? N by n factorial. Pi 0 for n is less than c. And then root to the power c by c factorial. Rho by c to the power n minus c into pi 0 for c less equal to n less than equal to capital K.
What is new n? New n, sir. 1 less than equal to n less than equal to c, then c less than equal to n. Yes, c less than equal to
Yes,
k.
c less equal to n less equal to k, no? N should vary from your 1 to k. See, you have here the state space is equal to 0, 1, 2 up to n. So I am saying that if the number of customers is n, okay, that is in the state space, no? So if number of customer is n, so then mu of n is equal to n times mu, where n is less than equal to c, because c is, you have the c number of service channel. Okay, like in your previous case. So in the previous case, if you look at here, so n greater equal to c, but there are infinite capacity. But I have now finite number of capacity. This is exactly similar things, but I have finite number of capacity there. Okay, so only thing is that I have the effective rate, effective arrival rate. In this case, effective arrival rate is basically same as your arrival rate because you have infinite capacity. But here, what I have said that if your system is full, that means if there are k number of customers in the system, so then it is forced to leave the system. Okay, that means the arriving of the customer is not allowed; it is blocked. Okay, so this is this part. So as I told you that this is the lambda effective in this case is lambda times 1 minus pi k, because pi k is the blocking probability. Okay, so the customers are blocked when the system is in state k, and hence the customers gets entry if the system is not full, and hence this is the lambda things are there. Okay, so Again, I can talk about what will be the average number of customers in the queue, which is my L of Q. This is by definition n should be C plus 1 to capital K, n minus C times pi over n. And then again you do these calculations. What I have, this is pi C rho by C summation over m is equal to 1 to K minus small c m into rho by c whole to the power m minus 1. And again, what is your L of S? This is LQ plus lambda effective by mu. Okay. And using your Little's formula, same thing actually I am just writing down again and again. TQ is equal to LQ by lambda effective, P of S is equal to LS by lambda effective. So whatever we have done so far, only thing is that I need to first think of what kind of queuing model it is. Okay, that means you need to model it. So if you understand that, okay, this problem lies in this model, and then the second question is then, okay, I have suppose say MMCK model. So whether stationary distribution exists or not, because if stationary distribution exists or under what conditions, then actually we are looking for the different kind of measurements, which is basically LQ, LS, TQ, and TS. Is it not? So that is more important. First, you need to recognize that your problem where it tends for, which kind of queuing model it is, or what are the applications of queuing model for this problem, and so on. And then you find out what will be your the stationary distributions of pi n using these formulations, and then you find out this TQ and TN and so on. So it is kind of easy, but you need to first look at the problem, you need to understand the problem, and you need to know that, okay, in where actually it falls, in which kind of queuing system it is. Okay. So for example, and then I'll stop. So I'll consider one example and then I'll stop it here. So a service center consists of two servers, each working at an exponential rate of 2 service per hour. If the customers arrive at a possession rate of 3 per hour, then assuming a system capacity of at most 3 customers, then the fraction of potential customers enter the system. Find the fraction of potential customer enter the system. So let me write down. A service center consists of say 2 servers. Okay, so C is equal to 2, each working at an exponential rate of 2 services per hour. Okay, so now the customers are arriving at a possession rate of 3 per hour. Okay, so assume that the system capacity is 3. Okay, assuming that, find the fraction of potential customers enter the system. Potential customers enter the system. Okay, so now this system, as I as you say that this is nothing but MM23 model. No, 2 server and then at most 3 customer can accommodate there. And what is your lambda? This is basically 3 per hour. This is 3 and mu plus. So mu, what I have, the 2 service each exponential rate of 2 service per hour. So mu is equal to your 2 in these things. Okay. So now what I need to find out to find the fraction of potential customer enter to the system. That means it is same as to find the probability that the system is not full. Then actually it will come, no? So now the fraction means basically later on actually we try to look at maybe in terms of percentage or something like that, or if you just keep it, that is also fine. The probability actually we are looking for. So the potential customers enter to the system. That means I need to find out what is the probability that system is not full. So the probability that system is not full, this is nothing but 1 minus pi 3, is it not? So these things, so need to find out 1 minus pi 3. Okay. So what is your pi 3 now? In this case, this is the blocking probability. So now you check it that pi 3, it should be 9 by 32, 2.5 plus 9 by 8 summation over j is equal to 0 to 1, 3 by 4 to the power j, and then inverse. That is your pi 3, and then this is equivalent to 0.0629. Okay. This is your pi 3, and then you need to find out 1 minus pi 3. So from there actually you will find out 1 minus 0.0629. Okay, so pi 3 actually I just write down the definitions from there actually got it. No, because this one is pi 0 and then I have pi 3, from there I wrote down. So this is pi 3, so 1 minus pi 3, this is the blocking probability, and then you can just put it in a percentage so that you will get it. Okay, so I'll stop now. And so this completes the whole courses. Okay, so please go through these things, and if you have some problem, please let me know. Then or if you think that you need again some discussion for some topics or something like that, so please let me know. Otherwise, officially I'll stop whole this syllabus here. Okay, so I just stopped my recording.